Hello everyone, I once again welcome you all to MSB lecture series on interpretative spectroscopy. So in my last lecture I was discussing about chemical shifts and how a chemical signal we get in NMR for a molecule is denoted as chemical shift, and what are the implications and why we call it as chemical shift, and what are the information signals give. All those things we discussed. Let us continue from where I had stopped. In my last lecture, I did mention about some of the chemical shift values for different type of protons in organic molecules. If you can see here, in methyl groups in alkane resonate at 0.9 ppm, whereas methylene groups resonate at 1.3, and methane groups CH shows chemical shift at 1.4, and when methyl group is next to a carbonyl group, it comes around 2.1, and next when acetylene carbon bond hydrogen resonates at 2.5 ppm, and then when CH2 is next to halogens or oxygen, the chemical shift comes around 3 to 4 ppm, and then in alkenes the chemical shift due to H comes around 5 to 6 ppm, and similarly methyl groups comes at 1.7, and aromatic region in phenol comes around 7.2, or even benzene for that matter, and in case of toluene, methyl groups resonates at 2.3 ppm, and aldehydic hydrogen comes around 9 to 10, and then acidic carboxylic acid H comes around 10 to 12 ppm, and in alcohols, alkyl alcohols OH groups comes at 2 to 5, and whereas in case of aromatic alcohols or phenols, it comes around 4 to 7 ppm. In case of amines, H on nitrogen resonates in the region 1.5 to 4, or it can go further depending upon the type of substance we have and also the nature of the molecule. So now here I have given a different nuclei having spin, nuclear spin I equals half, and also I have considered hydrogen with instrument frequency 100 megahertz, and you can see what is the corresponding frequency for different nuclei, all having nuclear spin value of I equals half, and also I have given natural abundance here. H is 99.9% and it is 100 megahertz, and the standard we are using is tetramethacillane. In case of 13C also we use tetramethacillane. Then if you compare the frequency, this is 1/4 of it, and similarly when you look into 19F, its abundance is 100%. We don't have any other nuclei other than 19F. So here the frequency corresponding to 100 megahertz in proton is 94, and similarly you can see here for 29 silicon, 31 phosphorus, 77 selenium, 103 rhodium, 117 tin as well as 119 tin, and 129 xenon, 183 tungsten, 195 platinum, and 199 mercury. So all these things corresponding frequencies are given here, and this gives you approximate ratio. From that one you can calculate, if the frequency is known for hydrogen, you can calculate the corresponding frequency for other nuclei. And also I have given the standard references for some of these nuclei when we are using in NMR. So now before I proceed further, let us try to make us familiar with the equation I showed you. That equation is, you just recall, H nu equals 2 pi nu. This is nothing but omega. Omega will be, we have to add 2 pi nu, so then it becomes, when you substitute for this one here, this will be equal to gamma H into B naught. So now this H will cancel, so then what we left is nu equals gamma B naught over 2 pi. So this is the equation we are going to use in NMR extensively. So let us try to understand the utility of this equation in calculating the precision frequency or Larmor frequency for different nuclei placed in a magnetic field of different magnetic field strength. So now one such problem is here. You can see here calculate the radio frequency necessary for the transition of 11 boron nucleus at a magnetic field of 10 Tesla. So, you use this equation. Of course, here what is required is you need to know this gyromagnetic ratio that is given here, and also 10 Tesla is given. Simply use this equation here. So, nu equals gamma value, let me write here, 8.584 into 10 to the power of 7. This is 10, 2 into 22 by 7. So, now if I simplify this one, it will become 8.584 into 10 to the power of 8 into 7 by 44. On simplifying this one, what you get is 136.5 megahertz. So, this is the radio frequency necessary for the transition of 11 boron when it is placed in a magnetic field of 10 Tesla. So, you should be able to calculate this one. Of course, here it 10.6 comes, it is 136 hertz it comes. If you remove this 10 to the power of 6, it becomes 136 megahertz. Okay. And let us look into one more example so that you will become more familiar. So, the other two problems I have shown here is if the radio frequency of approximately 200 megahertz is required for the transition of 31p nucleus and 400 megahertz required for the transition of 1H nucleus, calculate the applied magnetic field strength in Gauss as well as in Tesla. So, you should remember 10,000 Gauss equals 1 Tesla, that also I have given here. So, conversion. So, let us do this one. Now, again here use the same equation, nu equals what we have is now gamma over 2 pi into B naught. So, now we know this is known, gamma is known, and we have to find out B naught in case of 200 megahertz phosphorus NMR. So, this is 200. 200 megahertz can be converted into 200 hertz. So, this equals phosphorus gyromagnetic ratio is given here 10.840 into 10 raised to 7 into B naught, and now again 2 into 22 by 7. So, on simplifying this one, it will become 200 into this 22 into 244 into 10 raised to 6 equals 10.840 into 7 into 10 raised to 7 B naught. So, then if you simplify this one, what you get is 1,15,000 Gauss you get it. So, this can be nothing but 11.5 Tesla. So, this is the magnetic field, and this corresponds to 500 megahertz instrument. Okay. This corresponds to 500 megahertz instrument. So, this corresponds to 500 megahertz instrument. So, you can, I have given earlier this table of conversion of magnetic field strength and the corresponding frequency. You can just check from that data. It comes approximately 1,15,000 Gauss, that is nothing but 11.5 Tesla. This corresponds to 500 megahertz instrument. And if the 400 megahertz instrument, 31p nuclear requires about 161.2 megahertz radio frequency. Now, let us look into the second one. The second one is 400 megahertz for 1H. So, the same you can do it again, use the same equation, gamma into B naught over 2 pi. So, this is 400. So, simply I can write it here 44. This equals gamma is given here for proton, this is 26.753 into 10 raised to 7, and then this 7 whatever was there, it goes here. So, this is nothing but 2 into 22 by 7. So, 7 comes here and 2 is going here. So, that is what I have written here into B naught. So, simply now B naught can be calculated from this one, 400 into 44 divided by 26.753 into 7. So this will give you into 10 to the power of minus 7. So then when you convert into megahertz, what you get is you get approximately 9.39 Tesla, or that's equal to 9.4 Tesla. So that means basically 94,000 Gauss. So this is the magnetic field strength for this one. So this is how you should be able to calculate. Let's move on to further discussion. Okay, now let's look into the aromatic protons. For example, if you take a benzene molecule and subject it to NMR, what would happen to its chemical shift? We all know that the chemical shift range is 7 to 8, and why that happens you can see clearly here. And of course, here also we should look for all possible orientations of benzene molecule in a magnetic field strength of B0, and then if you take average of all of them, you can consider only two possible orientations. One is perpendicular, one is parallel, and here I have considered perpendicular one. In this one, the circulating electron density would generate a magnetic field, or induced magnetic field generated because of circulation of electron density in the benzene molecule under the influence of B0 generates a magnetic field that is aligned with the magnetic field B0. You can see the direction shown here. Okay, this is aligned with the magnetic field. As a result, what happens? The net magnetic field experienced by the protons in aromatic molecules would be going to high frequency shift. So that's the reason we call it as de-shielding. And then how about the parallel one? So parallel one you can consider here. So you consider like this molecule here, and here the little circulation of induced magnetic field can be seen, and little circulation of electron density, and hence whatever the magnetic field generated can be totally ignored or neglected. So that means not much contribution is coming from the parallel orientation. The bulk of the influence of electron density that generates say induced magnetic field comes in the perpendicular orientation, that is responsible for pushing the protons into de-shielded region of chemical shift range 7 to 8 ppm. So now let's look into vinyl protons. Again, vinyl protons I have considered the perpendicular one, and in the parallel orientation same thing is observed what I had described in case of aromatic molecules. So in this perpendicular one, what would happen? Again, induced magnetic field is acting in this direction, that is it is reinforcing the applied magnetic field. As a result, net magnetic field experienced by vinyl protons is much more compared to the protons in the absence of induced magnetic field. As a result, the net effect is de-shielding. So they appear in the range of 5 to 6 ppm. And again in this case also, perpendicular orientation has little circulation of electron density, and hence there is not significant magnetic field developed because of this effect, and hence that can be ignored. So now let's consider aldehydic proton. Again in this case also we can ignore the parallel orientation where the induced field magnitude is negligible. So we have to focus on again the perpendicular orientation. In case of perpendicular orientation, again this group is attached to electronegative oxygen atom. Again in this case also the induced field generated because of this ring current that is produced is aligned with the applied magnetic field. Here you can see applied magnetic field. As a result, the net effect is de-shielding or shifting the signal to high frequency, and it appears in the range of 9 to 10 ppm. And same analogy holds good in case of accelerating protons also. Here the parallel one is what dominates here, and in this case because of the alignment of hydrogen protons in this way, the induced field whatever that we are seeing is opposing the applied field, As a result, what happens? We see the net shielding in case of accelerating proton, and hence the chemical shift appears in the region of 2.5 ppm. And then if you consider the perpendicular orientation, again here in case of perpendicular orientation there is no significant contribution from Bi developed here, so it can be ignored. Okay, only the parallel one is what matters here. So once if we know these facts, it's very easy to understand why a given molecule nuclei are shielded or de-shielded, or appear in high frequency region or low frequency region. What would happen to the OH and NH protons? Chemical shifts of OH and NH depends on concentration, very important. Hydrogen bonding in concentrated solutions, de-shield the protons. So, signal is around 3.5 for NH and 4.5 for OH. So, that means if considerable hydrogen bonding is there, that results in de-shielding of the protons involved in hydrogen bonding, and hence the chemical shift due to NH protons or OH protons would shift to respectively for 3.5 ppm and 4.5 ppm. So, that means hydrogen bonding is there in molecules in solution, and one should be able to diagnose and tell approximately to what extent the hydrogen bonding is there by just simply looking into the chemical shifts of such molecules. So, the another reason for broadening of this OH and NH peaks in NMR is because of proton exchange between the molecules. So, now let us look into carboxylic acid. So, acetic acid is here I have considered, and delta 11 for OH comes here. Okay, this is for OH, and whereas for CH3 it comes around 2.1 here, and you can see here considerable de-shielding is observed for carboxylic proton and appears at 11 ppm. So, now look into another molecule here. We have three different type of protons are there. So, one is next to carbonyl group, another one is next to oxygen, and another methylene group is in between two carbonyl groups, and the corresponding chemical shifts I have shown. This one comes around 2.25. So, this is here, and then this is 3.41. So, this is here, and then this one is here. And again what you should notice is equivalent hydrogens have the same chemical shift. That means all hydrogens present on this carbon show single resonance, and similarly all hydrogens present on this carbon show single resonance, and all hydrogens present on this methyl group also show single resonance. Okay, you should remember, we will come back to looking into why they are equivalent and whether there can be some non-equivalence, and hence we can see some interaction of the hydrogen atoms present on the same carbon atom. So, now let us look into the importance of intensity of signals. You can see here in this molecule we have two type of hydrogen atoms are there. I have designated with blue color and H color here. This is one methyl group is there, and here on this carbon we have three methyl groups are there. And then if you just look into the signals, by simply looking into the intensity, you should be able to tell which signal is for which group. So, this one shows chemical shift here, and this one shows chemical shift here, and if you just measure the intensity, it is almost 3 times. If this is say this quantity is there and this is about 3 times here, you can see here 3 times 1, 2, 3. So, that means basically the intensity what we see can also tell you about how many such groups are there and how many protons are there, so that understanding the structure and elucidation of the structure becomes rather easy. Okay, now, I have simplified here. In the graph you can measure and you can see the intensity here, and then you can show here, and up to here if you go, it can clearly tell you about here 9 protons are there and here 3 protons are there. That means it is 1:3 ratio is there, that could be clearly seen from this one. So, that means intensity, looking into the intensity is very important in identifying similar type of groups in the molecule. Okay. So, the area under each peak is proportional to the number of protons. This is shown by integral trace. This is what we call it as integral trace. Usually you can get this information directly from NMR spectrum. So, now let us consider this molecule here, and now let us see, here we have 3 protons are there, here 2 protons are there, and here we have 1 is there, and then we have here 6 are there. Okay. And that means basically 1, 2, 3, 4, these 2 are 1, and this is 2, this is 3, and this is 4. 4 type of groups are here, and we should have 4 signals. Of course, 1 is here, 1 is here, 1 is here, 1 is here, and just by looking into the intensity we should be able to tell these 2 will be corresponding to this one. And now CH2, CH3 is there, CH3 will be coming to this one, and then CH2 will be coming to this one. So simply by intensity you should be able to tell. And then values are there, so you can clearly see now where exactly these signals are located. And this is the integration. So far whatever we saw only single signal. Do we see always one signal no matter how many protons are there, how many nuclei are there? That is not the case. Now let's look into this term. What is spin-spin splitting? So non-equivalent protons on hydrogen, non-equivalent protons on adjacent carbons have magnetic fields that may align with or oppose the external field. You should remember, when we are subjecting a molecule to the magnetic field under NMR conditions, if we are focusing on, let us consider a ethanol molecule here. So when I am focusing on this one, this methyl group, and of course here methyl group, what happens, circulation of electron density also induces a magnetic field, and that can be aligned or oppose the magnetic field. Based on that one, we get a chemical shift at some reason. So but on the other hand, when these protons are persisting, the neighboring would not keep word, they will also be persisting. As a result, what happens, whatever the induced magnetic field they generate can also influence on the chemical shift of this one. And to what extent they influence depends on whether they are aligned with the magnetic field or opposing the magnetic field. So that means the neighboring protons can split the adjacent protons and adjacent carbon atom depending upon how many such protons are there and how they are aligned or how they are behaving in the magnetic field. So this would leads to the term called spin-spin splitting. As a result, signals would be seen as multiplets. So that means this magnetic coupling causes the protons to absorb slightly downfield when the external field is reinforced and slightly upfield when the external field is opposed. So that means whatever the magnetic field they are generated can be something like this or can be something like this. If they are something like this, you can see signals are more de-shielded, and if they have something like this, shielded. So this is how they can influence, and that means all possibilities should be considered, so signal is split. So now another useful property, that means now I am giving some more details about spin-spin splitting. So another useful property that allows NMR spectra to give structural information is called spin-spin coupling. So which is caused by spin coupling between NMR active nuclei that are not chemically identical. If they are chemically identical, what would happen? You will see only one signal. For example, if we take ethane molecule, two CH3 are there, they are chemically equivalent, and you will see only one signal. But if you take CH3, CH2, OH or something, CH3, CH2, Cl, then the neighboring ones are different. So then you can see interaction between them, that what we call it as spin-spin coupling. So different spin states interact through chemical bonds in a molecule to give rise to this coupling, which occurs when a nuclei being examined is disturbed or influenced by a nearby nuclear spin. So in NMR spectra, this effect is shown through peak splitting that can give direct information concerning the connectivity of atoms in a molecule. Nuclei which shares the same chemical shift do not form splitting peaks in an NMR spectra. So this is very, very important. In general, neighboring NMR active nuclei 3 or fewer bonds away leads to this splitting. This splitting is described by the relationship wherein neighboring nuclei results in n+1 peaks, and the area distribution can also be seen from the Pascal triangle. So however, being adjacent to a strongly electronegative group such as oxygen can prevent spin-spin coupling. So that means in between two methyl groups, if you have oxygen, that can prevent the interaction of these two groups. For example, a doublet would have 2 peaks with intensity ratio of 1:1, while a quadret would have 4 peaks of relative intensities 1:3:3:1. This information comes from Pascal triangle. The magnitude of the observed spin splitting depends on many factors and is given by coupling constant J, which is in units of Hertz. So let us discuss more facts and look into more examples to understand in a better way spin-spin coupling in my next lecture. Until then, have an excellent time reading about spectroscopy. Thank you.